So I'm going to talk about the biological path toward strong AI. I'm an open source community manager as well as an engineer at a very small company we still call a startup named Numenta. So I'm going to give you some context first. I'm going to talk about intelligence at a high level, strong versus weak intelligence, and then we're going to talk about some minor brain science. We won't get too crazy, which will introduce the concept of hierarchical temporal memory. Has anyone ever heard of this HTM, hierarchical temporal memory? Great. So I'm going to describe that, the key concepts behind this theory of intelligence, and describe how the algorithms work with visualizations. But first, about intelligence. So I read this back in early 2015 in the title of a Wired article, and I had to do a double take because I was like, no, it hasn't. But I realized that my definition of intelligence was different from a lot of other people's definition of intelligence in the field. So if I modify this to say weak AI has arrived, I would agree with this statement. Not that I have anything against weak AI. We can do really amazing things with artificial neural networks today. A lot of these talks that you've seen in this conference are about all the amazing things we can do with it. We need this technology. I'm not belittling it in any way, but I do think there are some things about weak AI that is misconstrued. I don't think weak AI is intelligent. Some people think plants are intelligent, so maybe along those metrics they are. But my definition of intelligence is a little bit stronger. I would go along with the definition of intelligence that Wikipedia lists for AGI, artificial general intelligence, in that something that is intelligent can reason, have strategy, represent knowledge, plan and learn and communicate, and the kicker, integrate all these things towards common goals. So individually, we may be able to make weak AI systems that are able to do some of these things, but the integration of them to perform common tasks in a general way and context switch from situation to situation, I don't think our current weak AI technologies will get us there. And I can tell you why. I think there's some things missing, some crucial things that are missing from weak AI, current technologies in AI. The first thing is realistic neurons. So all of the artificial network, or excuse me, the AI tech, the deep learning, convolutional neural networks, all the stuff that you're hearing about today and in this conference are originating from this artificial neural network neuron that was created decades ago. And when you compare it to what a real neuron does, a pyramidal neuron in the neocortex, it's really lacking in capabilities. But we've built some really amazing things with this very simple neuron model. So it does hint at maybe we should investigate more about how the neuron works and understand how it works so we can try and build more intelligent systems. So I believe you need more realistic neurons to build things that are truly intelligent. And another big thing that a lot of people don't talk about is you need something to have the ability to explore its environment. Everything that is intelligent today has the ability to explore its environment. You can't have intelligence, in my opinion, by having something just sit and be fed data. It can learn a lot from that data, but I don't think it's going to be able to make intelligent decisions. Just think about a newborn baby. It's constantly moving, wiggling around. It's just randomly it's interacting with its environment, and it's learning all the time. And that's what we need to make systems that have that ability. You data scientists know that when you get a new data set, there's a lot of human exploration that has to happen so you can understand the different aspects of that data set. We need to build systems that are able to do that exploration without us prompting them. So I think movement is very important. So a bit about my company. This is what we're really primarily interested in, is how intelligence works. And we're focused on the mammalian neocortex for specific reasons. And we want to create software based upon those principles. Because we think to create intelligence, we need to study what we know is intelligent today. And the one thing that everybody, I think, can agree is intelligent is the mammalian neocortex. So we're going to start there. There's a lot of discussions about what's intelligent and what's not, but we all agree that our brains are intelligent. So let's talk about brains a little bit. So if you were to take the neocortex, which is that wrinkly thing on the top of your older brain, and spread it all out and flatten it out, it's about the size and shape of a dinner napkin. It's like 5 millimeters thick. And if you were to take a slice of that at any point and compare it to another slice of it at another point, you're going to see that it has a homogeneous structure throughout. So the cellular structure in one of these slices is going to be the same whether you're doing visual processing, auditory processing, motor command generation, whatever it is. Your cortex has a common algorithm throughout. So that gives us a key to try and find out how this is working. So what we've done, have been trying to do for years, is to try and model one layer, or excuse me, really one region. I don't want to get too far into neuroscience, but there's regions, layers, and there's 6-ish layers within a region. There's still some confusion about that. We model layer 2, 3, another point of confusion. But there's a lot of stuff going on in just one region. And so we make models of neural interactivity with a small cortical simulation that involves these pyramidal neurons. So I'm going to go into that. Each one of these little cubes in our model is a neuron that we model with some specific attributes that we think are important. First, this is my hand drawing of a neuron, but a neuron doesn't just get one type of input. It can get different types of input. I'm just going to talk about proximal and distal input. A proximal input is like feed-forward input that's either coming from some sensor modality or some other part of the cortex or the other part of the brain. Now, a section of cortex, when it gets proximal input, it has no idea where it's coming from because it's this algorithm that's running. It doesn't know if it's processing vision data, auditory data, whatever. It has no clue. It just knows that it's mapping onto this input, and that's what it sees changing over time. The distal input for pyramidal neurons are not coming from some sensory modality. They're coming from neighboring neurons within the structure. This provides context to the input. So before I get into some deeper stuff, I want to note that this is an evolving theory. We have tried to create a theory of intelligence based on the most recent neuroscience research that we can find, and we continue to evolve it as more research comes out. So this is an evolving theory based upon this neuron model that I just described to you. One of the key components to understanding this is understanding data format called sparse distributed representations. At its core, it's just a big binary array with a very small amount of bits turned on. Each bit has semantic meaning. It means something. So there's some overlap here with a lot of stuff that's going on in the ANN deep learning community with sparse coding as well. But I think of it like this. If you think about a fiber optics cable, like a giant fiber optics cable, that could have thousands of fibers in it. And at any one point, only 2% of them are on. 2% is important because we took that number from the brain. At any point of time, only 2% of your neurons are active. And that turns out to be really important. So if you took a nerve axon bundle, it's analogous to a fiber optics cable. So that's the input that might be coming into a cortical section. And it's just firings of neurons happening over time. The cortex's job is to try and make sense of that information without knowing where it comes from or what it means. So over time, it's looking at this firing. We call these sparse distributed representations. At every time step, we have a different firing that's happening temporally over time. So I'm not talking so much about spatial information. I mean, each time step is a spatial information, but it's the kicker is we're trying to understand them through time as they change. So I'm going to show you a couple of demos about SDRs that I think will kind of illuminate this a bit. So here's an example of an SDR. It's got 2048 bits, only 40 of which are on. That's about 2%. So this is what it might look like. And the capacity of this is surprisingly large. So this is a typical size that we use in our models. The amount of ways that you can fit 40 bits into this space is larger than the number of atoms in the known universe. So we're not going to run out of room, ever. So that, I thought, was surprising. And I'm going to also talk about classifications. Okay, I'm going to set this up and then explain a bit. So what I have here is like 100 SDRs, just randomly generated SDRs. They're all 2048. They continue off the screen. I'm just not displaying them all. Okay, so this is like a sample of each one of these SDRs. And from this random generation, I'm going to try and match, and I'm going to show you, I'm going to pick one of these, I'm going to add some noise to it, and I'm going to compare it to all of the SDRs that I've collected. And this takes a few seconds. And what we end up with is, this is the SDR that I'm matching. I've added 25% noise to it. So you can see right here, I can add more noise if we want. And let me try and make this smaller. Sorry, this ranking that I have here is that SDR compared to every other SDR. This is just a simple AND operation. It's just an overlap score. How many bits are similar? We can easily tell that that SDR, even in the presence of 45% noise, we can tell. We've seen that before. And we can handle a lot of noise. This is one of the properties I want to explain about SDRs. This is very noise tolerant. So I can identify that I've seen that SDR even in, and I can actually know exactly what my false positive rate is, 3.5 times 10 to the negative 15th. So it's not very often am I going to hit a false positive with this space of 100 SDRs that I'm comparing to. The brain is extremely reliant on this noise tolerance capability of this medium. So it's something that I like to point out. So this data format of SDRs, while it may seem bulky because we've got so many empty bits, it provides us with some interesting capabilities. Okay, so now I'm going to talk about encoders. So your retina is an encoder. It's a very complicated encoder. So is your cochlea, so are your somatic senses, your feeling. We're not interested, or at least Numenta, my company, we're not trying to create encoders. We're trying to understand how the cortex processes the encodings coming from the encoders. So your retina, your cochlea, they're always sending these stream of SDRs into your brain. And your vision cortex is huge, so it's spread out throughout a large, massive cortical space. And that's what's understanding what you're seeing all the time. The way the retina encodes this is very complex, and we're not trying to write that in software. But we do have some examples of encoders, very simple encoders, that I like to show to at least show you what I mean when I talk about SDRs requiring a semantic meaning. So I'm going to show you a date encoder. And this is going to seem really simple, but what I have here is I'm trying to encode the semantics of a date, a timestamp. I want to know what day of week it is. I want to know whether it's a weekend or not, the general time of day, and the season. So what I do is, and this is me going from today and skipping a week ahead. When I skip a week ahead, you see the season ticks. And I continue, the season continues to tick. When I move to Saturday, the day of week and the weekend change. So I'm encoding this timestamp differently depending on different features of the data point. And also I can change the time if I want to, so you can see that block change too. So down here, I've got the entire encoding. And you can see it change as well, because to send this into a region of simulated cortex, we don't have to have different regions handling different semantics that we want to extract. We just throw them all together. So we just concatenate these representations, and that is going to be what I call the input space to the next process that we're going to run. And let me give you a little bit of a more tangible example of this. So here is an example of an input space. Let's see if we make this smaller. So what I've got here is real data. It's just a stream of scalar values, each associated with a timestamp. And I am taking the actual scalar value, its power consumption at a gym in Australia. I'm going to encode the time of day and whether it's a weekend or not, and that's it. So just the scalar value, time of day, and whether it's a weekend. And as I hover through this, you can see as we go through these troughs and peaks, that first bucket of bits is representing the scalar value. So you can see going up and down with the troughs and peaks. And those other buckets of bits are what's encoding time of day and weekend. So this is giving me a representation of one scalar value moving with an associated time with each point. Now, there's lots of ways that I might be able to encode this specific data graph in an SDR format. Here's another way. Instead of using a scalar encoder that has a continuous bucket, we can distribute those buckets throughout the space. It still retains the semantics of the scalar value, but it looks a little bit different. And as you can see, as things go up and down, bits change, some don't. There's a lot of details to the encoding process that I won't get into, but I'll have some resources for you at the end of the presentation. But this is a typical input space that we might be looking at with the next phase of HTM, which is called spatial pooling. And so another structure I need to introduce in the brain is called a mini-column. So in a layer of cortex, the way the pyramidal neurons are structured is that they have this grouping in columns where, say if we were looking at an input space, like we were just looking at with an SDR that's changing over time, that's sort of what that green is. Each column has a proximal input from that input space. And all of the cells, all of the pyramidal neurons within that column share that proximal input. And columns become activated when their receptive field overlaps enough, their connections overlap enough with the pattern that's occurring in the input space. And I'll show you this in just a minute. So this is all about proximal feed-forward input. And the whole point of this is that it allows us to normalize the sparsity of the representation. So we can take an encoding that may be very erratic and chaotic, and we can normalize it, and it provides a space for the next algorithm to run that does sequence memory. So we are retaining the semantics. Let me do another demo here. Hello. I'm going to do connected synapses. Okay. So this is called spatial pooling, okay? So remember that three-dimensional structure I showed you, of cells like in a cube? So this is like looking down on top of it in the spatial pooler columns. So this input space is where the data might show up, and so it might look like this. This could be a possible encoding that's coming from somewhere. But I just want to show you how spatial pooling maps columns onto the input space. So for each one of these columns, and we can have many cells per column, it has a specific relationship with the input space. So this column in particular, these orange boxes are its receptive field. Those are the cells that it could create connections to. And the blue dots with the lines are actual connections. And this is pseudo-randomly initialized so that every one of these columns has some relationship with the input space. And this is a starting point for learning. I can even show you there are permanences involved here as well. So, for example, it's not just whether it's connected or not. We have a numeric permanence value associated with each of these connections. So that column has a specific relationship with every one of these cells, including a permanence value. And you can see ignore that. You can see the permanence value on that graph on the right. If it's above a certain threshold, we're going to call that synapse connected. And this is basically what its view is into the input space. Each one of them looks completely different. It has a totally different viewport of the input space. And these connections, these permanence values, degrade over time or increase over time depending on how well it's matching the input that's coming in. The next one, learning rules. So this is going to be a similar visualization, but at this time I'm showing you an actual piece of data that's showing in the input space. This is an encoded SDR. And I'm showing you at a certain time step, these are the columns that are active. And this becomes important in the next topic of temporal memory. So these columns are activating specifically because this column, for example, has enough of its connections with the input space overlapping with the current input that it has breached a threshold. So we basically take the top so many number of columns that have the most overlap with the input, and we turn those columns on. And then we can control the parameter so we can specifically tell it, okay, I want 2% density in this representation, or I can dial it up or down. We typically keep 2% because that's what we see in the brain, and it works. So like this representation, or this column, for example, does not have enough overlap with the input space to become active, but these all do. So that's how spatial pooling works. And over time, in the active columns, when they become active, their proximal segments are also incremented. The permanences are incremented, so they'll continue to activate based on that type of pattern or patterns that have a high overlap with that pattern. And the ones that don't, they get decremented. So this is called spatial pooling. The whole point is retain the semantics of the input, but put it into a space where we have more control over the representation's sparsity. Okay. Okay, so the next big thing is called temporal memory. So we've only talked about spatial stuff so far. All the proximal inputs are basically just spatial mappings of encodings to columns in a spatial pooling construct that learns over time and learns to represent that data better over time. Within each of those mini columns, there's another process happening as it sees input over time. And this is, we call it the temporal memory algorithm, but basically this is that distal context, this distal connections I'm talking about. The proximal is all about spatial input mapping to the input space. The distal connections give context to that particular spatial input and allows the cells to decide whether they think they might be next to fire based on the context that it sees. So it identifies the context because of those distal inputs, and this is like, these distal connections are happening between cells in the mini columns of the structure. So they can all connect to each other if they need to. But it happens all within the mini column structure. And it puts cells into predictive states for the next time step. And I wanted to explain this quickly with this. This is a comparison of the biological neuron model to sort of our software model of an HTM neuron. And here is the feed-forward input coming from the input space. And this distal context, one cell could be connected to one or many, it can have segments, one or many segments. And this is all neuroscience terminology. And each segment could have synapses connected to a bunch of different cells. Each one of these segments is basically a coincidence detector. So this cell could have a lot of segments at each time step. If it's in an active column, or scratch that, it can be any time step, whether it's active or not. It can look across all of its segments, all of its distal segments, and decide if any of them breach a threshold, and it puts itself into a depolarized state, which means it thinks it's going to fire next. Question?
How did you decide what the distal connections between the columns are going to be?
So initially, there's a pseudo-random initialization. So actually, I don't think there's any connections initially, but there are like branches reaching out. So there's permanences between these distal connections as well as the proximal connections. But we start them all, I believe, disconnected, and they grow over time. So let me do a demo. Yes?
One question related to what we are asked. So is it like you learn those connections over time? Is there a feedback mechanism?
You learn the connection over time, but there's no feedback mechanism as of yet. That's a part of the theory, but we're not working on that part of the theory. The brain's really complicated, turns out. So, I mean, honestly, we have spent years researching layer 2, 3 of the neocortex, and there's 6 layers. So we're just getting into researching like layer 4 and 5 and trying to figure out what they're doing. I'll talk a little bit about that, but the whole idea of feedback and hierarchy, while we haven't implemented hierarchy in the past, we're not even paying attention to hierarchy right now. We just want to get that one layer working the way we think is biologically plausible and is doing something valuable, that we believe the same way the brain is.
So is there some mechanism which helps learning these connections?
Yeah, I mean, when the predictions turn out to be right, then that reinforces the connections that it had to those distal components. And when it's wrong, it decrements them. So let me give you, this is sort of a big demo. But OK, so what I've got here is a note sequencer. You can hear these playing. C#, A, E, F, over and over and over and over and over. It's a 4-note sequence that I'm just playing over and resetting and starting over. This is the input space in green. And so it's a really extremely simple encoding. I'm just taking blocks of the input and turning them on for each note. The bottom one that's never showing up is a rest. And this structure is the mini columns in the spatial pooler, okay? So let me spread this out. You can see the columns now, right? These are the active columns. These active columns, if you look closely, for each one of these inputs, the same columns are firing. The same columns are becoming activated. And it's representing the same semantic data as the encoding is in the input space. So that's the spatial pooler working. Now I'm going to show you cell activations. So this is the temporal memory algorithm now working on top of the spatial pooler. And let me explain a couple things. There are two ways that a cell within one of these mini columns can become active. The first way is when an active column occurs, we look at each one of the cells in the column, and if none of them are in a predictive state, if it's completely, this means that it's an unexpected input, nothing is predicting this to happen, then we'll activate every cell. That's what you see right here. We call this bursting, and it's a neuroscience term, this bursting. So every cell bursts, and what this represents is either the start of a sequence that we haven't seen before, or a branch of a sequence. So we were in the middle of a sequence and something unexpected happened. This is one way of sort of kicking off a sequence. The second way and I'm going to turn on some different cell states here. The second reason that a cell might activate within a mini column is if it is in a predictive state. So we'll look through all the cells in the mini column, and if any of them are in a predictive state, then we'll activate it. That means basically that it was correct, because the predictive ones, and I'm showing these cyan ones, these are in a predictive state based on the last time step. So these think that they're going to fire next, or actually they thought they were going to fire next, and then this happened, and they are all in the predictive state, and the active columns that they predicted were represented, so they become active. Yes?
Do the distal connections of a given cell within a mini column, do they connect to every layer of depth of the mini column, or just their neighbors that are the same slice of depth?
So yes, every layer of depth of the mini column, yes. They can connect to any cell in that structure. Now, when you start talking about the biology, I mean, there's a lot of fuzzy lines going, because I've basically cut out a small section of cortex and not allowed it to play with any other cortex around it. So there's some fuzzy areas here that we find it hard to model. But for the sake of this model, any cell could potentially have a distal connection to any other cell. And also, those distal connections don't have to come from cells in this region, which that's a different story. But okay, so the second reason was because the cells were put in a predictive state. How do cells get into a predictive state is the next big question. So I'm going to show you, based on this input, these are the cells. Let me turn this on. So based on this input of these yellow active columns and the active cells within those columns, these blue cells think they're going to fire next. What these blue cells are really representing is an E, because they've seen C#, A, E a bunch of times by this point. So when we get to C#, A, which is represented by the yellow and the orange, then E comes next. And all of these blue cells think they're going to be next because E is coming next. And the reason is, if I click on one of these, is each one of these predictive cells that are now depolarized, put into a predictive state, have a segment that is connected to all of those A cells that we just saw fire. All of these other cells have no connections. But every one of these blue cells is connected to basically the A cells that are currently shown. So if we move forward one step, you're going to see all of these blue cells turn orange, right? So it was correctly predicted. Now these blue cells are predicting F#. If we move forward, those turn orange. At the end of the sequence, there are no predictions. Because like I said, I'm just setting in 4 notes and cutting everything off. Setting in 4 notes and cutting everything off. Yes?
So there's extraordinary combinatorial complexity in the possible distal connections.
Yes.
How is it deciding that those distal connections are the ones that it should be looking at?
Well, for each time step, whenever a cell is activated correctly, let me move forward in the example, and I think I can explain it a little better. So I'm going to keep playing this. I think it's learned it pretty well at this point, so I'm going to stop at A. Okay, so we're at A, and all of the E cells are about to be activated. They're predictive, and they're going to be activated. But I'm going to change this now, and I'm going to make it a C#. So what's going to happen? Anybody know? What's going to happen when we move forward and those E cells are not going to fire? Those columns won't fire. Bursting. So next time step, we see a completely different set of columns activate that we didn't expect. We see C# columns activate. That's never happened before. So bursting occurs because we've got a new sequence. First we had C#, A, E, F#. Now we've got C#, A, C#, I don't know. At this point, this sequence can branch. So this mechanism of bursting allows us to branch out to other sequences. And let me turn some of this color off. And I'm just going to keep running through this. It's going to take it a while. But I'm trying to train it a little bit on this new sequence now, so maybe it's got an idea about it. So let's go back to A. And now I'm going to show you the predicted cells. And you might notice that there's about twice as many, right? Because it's predicting C# and it's predicting E, because it's seen both of those patterns before. And actually, I'm going to show you the correct ones and the incorrect ones. So you can see half of them are correct because it was guessing C#, because that's the pattern it's been seeing, and the other half are wrong, and those are the E cells. So your question about learning is, there's punishment happening for these incorrect cells. So segments, distal segments will grow to connect to more cells as cells activate because of proximal input. So cells activate only because of proximal input. The first thing that kicks them off is the bursting. And after they're bursting, and we've got context going on, because we have to let it run for a while before the segments start growing. So you got to sort of think of it as a newborn brain. You know, it's got no connection. It's got the wiring set up, but it doesn't have any reinforcement for anything. So we have to let it play for a little while before it can actually start seeing the patterns. And as it's correctly predicting things, it's reinforcing that pattern, and otherwise it's unenforcing it. Yes?
How is it seeing the pattern? How is it then deciding that there needs to be a distal connection between that green or that green and that?
So that's a mechanism of bursting, actually. So within, and I don't know a ton about this area of the theory, but bursting will activate those cells, but it also sort of randomly chooses one cell to represent that new pattern over time. So I think that's where you get those connections starting, because that's reinforcing a connection to an existing cell, right? So I think that's how it starts. Yes?
So it looks like each predictive state is based on a previous state, but how does it know that it's seeing a C+ that was preceded by an A?
See, that's the thing. Each state doesn't just show you the previous state. It shows you the history. So this state that I'm in right now, let me just show active cells. This state of I'm going to go back to it. Well, here we're in the C# area, but these active cells right now are representing not just C# following A, but C# following A following C#. So that context of the entire pattern is followed through as patterns get created. So this combinatorial effect is really relevant. So there's some other experiments I can show you, but I'm probably going to run out of time. Think about this. There's four words. Boys eat many cakes. Okay, the temporal four word pattern. Girls eat many pies. The two in the middle, the eat many, are spatially exactly the same. But if you were to train it, boys eat many cakes over and over, and then you train it, girls eat many pies, and then you give it the spatial representation of many, it will activate the cells that mean girls eat many and boys eat many. Does that make sense? Okay. All right, so I'm running low on time, and I want to take some more questions. So I want to reemphasize, we believe these are the foundational components of neocortally inspired intelligence. There's a lot to learn from the brain. Like I said, there's many parts of the brain. We're talking about just one part, the seat of intelligence, which is the neocortex. And there's lots of stuff going on in the neocortex that we still have no idea about. And when I say we, I mean humans. So there's a lot more to learn here. But I think that we're on the right track to trying to understand at a very low level how intelligence works and how we can build things with it. We are currently working on research involving sensory motor integration. Like I mentioned, movement. We believe that's a key component in intelligence. Layer 2-3 does this sequence memory that I just described here, but the same mechanism, the same distal connections, proximal connections, that same algorithm that I was talking about that does cell activations, works in layer 4 to do allocentric object retrieval. But the distal connections don't come from the same area of cells. They come from motor commands and other places. So we're researching that area, and we still think there's a lot that we can do here. If you like these visualizations, they're all from a YouTube series that I did about how HTM works called HTM School. You can Google it. It should be the first thing that comes up. These go into a lot of detail, and if this isn't enough detail, we have papers on Numenta.com about this tech. We're working on more papers about how columns and layers work. Some of these are silly, but they should be entertaining. But lots of stuff about SDRs, spatial pooling, temporal memory. And remember, this is all of our code is open source. We've got a decent community that I'm sort of the head of. I'm always on our forums. You can go to numenta.org to learn more. If you have any questions, I will answer them. And I think that's it. One more thing. If you want to hang out with some people from our community, I am having a little HTM social hour tonight in my hotel. Not in my room, but I've got a room at the hotel. So come grab me later. I'll be walking around a little bit if you want to come. It's just going to be 10 or so people that are on our forums that wanted to meet while I was in Boston. So let me know. Otherwise, I'm happy to take questions. Yes? The methods we use for neuroscience research. So we don't do the research. We read the research. And then our research is about how, okay, so a thing about theoretical neuroscience. There's not many people doing theoretical neuroscience. And our founder, Jeff Hawkins, found that to be the case 15 years ago. And he founded a Redwood Neuroscience Institute to do the research. And since then, there's been a lot more advances on how we understand specifically neurons to interact with each other. So they read a lot of papers. Currently, they're really interested in grid cells, location cells, place cells, these things that denote locations of things in time and space. So we do try and influence what papers get written, but we're not the ones with the wet labs, and we have to leave that to like the hardcore neuroscientists. We do have a neuroscientist on our team, but he helps us implement software to prototype things and how we understand intelligence to work. Any other questions? Yes? Absolutely. Yeah, it's like a sequence that's seen over and over and over. That just gets wired in because the permanence values between those distal and proximal connections just get weighted higher and higher. And it does forget over time. And those parameters are all tunable. If you create a model, you can tell it to increment at a certain rate or decrement at a certain rate, distally and proximally. Yes, definitely. This is an online learning system. This is something that once you establish what the data format is and how it's encoded into SDRs, you can stand a system up that will handle that data format even as it changes dramatically over time, as the patterns change. If the data type changes, we have to create a new model. But as the patterns change over time, it will adapt to them. Yes?
You mentioned theoretical neuroscience results as what it means with this, but is most of what we saw today also grounded in empirical or experimental neuroscience?
Some of it is theory, and some of it is not. And a lot of this is some of the things I've described to you, like cells going into a predictive state. The implementations of this stuff is as our discovery, like Niminta's discovery. And some of it is conjecture, honestly. We think this is how it works. We don't have any hard and fast scientific journals to back it up, but we're not going to let that stop us from continuing to theorize on how intelligence works and try and get it. So we adjust as new research comes, and we try and adapt our model to fit it. In the back there, sorry. Our biggest success has been in anomaly detection for streaming data over time. So we've got a good set of parameters for like one model for a scalar, just a scalar piece of data that's changing over time. And as long as there are patterns that fit the human descriptions of time, as like hour of day, day of month, season, the type of stuff I was showing you, we do a pretty good job of identifying anomalies that occur like in server data or in like power consumption, like you saw there. So that's probably our most promising application. And we have one partner called Grok Stream that has a IT analytics product that runs NuPic, which is the code base that is the HCM implementation. So definitely analytics and anomaly detection is a big one for us. Yes?
When neurons form distal connections, do they privilege nearby neurons, or do they check?
In our model, we treat all neurons within the structure as the same. But in a realistic model, there's topology involved. So there will be more privileged connections to things that are closer. I've got some visualizations of topology. I've played around with it a little bit. We don't even use topology now because our data is not rich enough to take advantage of it. But it's definitely a crucial part of the theory, and we can't throw it out. So we've implemented it, and we don't use it. Yes?
So if the human brain is a product of evolution, would it be possible to use evolutionary algorithms with, building blocks and the right simulation to sort of simulate
You're welcome to try. That might be a good approach to trying to develop encoders, because our encoders have had millions of years to evolve into these really complex systems. Like, does anybody research the cochlea? I thought this would be easy. It is not easy. There's a lot of stuff going on in your cochlea that creates those activation patterns that your cortex sees, and it's not simple. Somebody had a question over here? No. In the back? Yeah, absolutely. Well, the sequence memory happens in layer 2-3. So when you get input to a cortical region, all of the layers are going to get that input in one way or another at the same time, and they work together to try and put the picture together. So we're just modeling the sequence memory. That's what I showed you today. But once we add more layers to this model, like to do object recognition, for example, that's going to get the same feed-forward proximal input, but its distal connections might come from different places. Yes?
I was wondering if it implements any kind of neoneurogenesis where we can randomly increase so that new connections form?
I don't think so. That being said, there's no reason somebody couldn't experiment with that. So yeah, I don't think so. Yes?
You mentioned that you viewed movement as a state of intelligence. Does Niminta do any work, or are you planning to do any work with human interaction, or do you think there's any potential for learning from computer interaction?
First question, no. Second question, sure. I think there's a lot of potential, but we're not working on it. Yeah. That's a hard problem. I think Mr. Musk is simplifying it too much. That's a very hard problem. Yes, in the back. I'm sorry, can you speak up? The mouse pointer? Oh, it's called mouse pose, the little highlighting thing. Yes. Yeah, they're on online, and it's called HTM School Viz. This is dirty code, man. It's not as good as you'd think. Yeah, but it goes off track really easily. So we don't typically do that. We can, I don't know exactly how we do this. We use typical classifiers to try and get output out of the system based on cell activations. So a predicted state, like I would show you, should be mapped to some encoding, right? That we can then turn into a value and how that got encoded. So I don't totally understand how all that jazz works, but we can predict not only like one time step in the future, we can predict n time steps in the future. Of course, they get worse and worse the farther in the future you get. But that's based on the knowledge that the system has of the current sequences it's in, and what the probabilities of where it's going to be n steps into the future. There's sort of a missing component here that I didn't talk much about called temporal pooling, which is a way for us not to just get those probabilities out, but actually identify the specific sequences we're currently in. And that turns out to be a hard problem. Okay, any other questions? I guess we have time, so. Sure. Go for it.
Can you use this to like analyze a static image and like scan through it? Pinpoint?
That's a good point. So we've experimented with that. So this method is not good at just static image classification. This is not, I mean, your brains are really good at image classification, but this model that we have is not. Something else is going on that enables that. But the idea of a saccade, which is the way your eyes move, like so many times per second without you even knowing it, is important, because that's how you analyze a scene. Your retina gives you a high-resolution image of the very center of what you're seeing, and it's very low resolution otherwise. That's why you're always bouncing around. But in order to get this right, you have to have motor commands involved. They have to have motor command feedback, because if you're bouncing around and you don't have that, your cortex is going to have no idea what those images mean. It's going to be random images that it can never put together. But if it has a motor command to know where your body orientation is and where your eyes are moving, it can tell because it told it to move there. You had a question?
Yeah, so I was wondering if you could explore the possibility of taking these models and applying it to like the types of synthetic, neurosynthetic chips that I believe it's IBM that's recently developed.
Like wafer scale type, yeah. So we've thought about that, and we have been in communication with several different companies that are making, chips of the future, and they're thinking about this as well. I don't know much about that area, but for this to become like a big thing, we have to have hardware to support it. And current hardware, even GPUs, won't support it because there's required plasticity between these computing units, these neuron units. That don't exist today in silicon. So whether the wafer scale thing, so my boss thinks it's promising, but that's all I can tell you.
How is sparsity enforced?
The spatial pooler enforces sparsity. So the encoding that's coming from your senses doesn't necessarily have to be sparse, but it has to have semantic meaning. That spatial pooling step where each column is trying to represent different parts of that input space, that's what enforces sparsity. So, and you can control how many columns are active at any point in time.
So does it do like a rank order of all the neurons that are in predictive state and graph the top and highest?
Yeah, let me correct that. It does a rank order of the columns that are active. This isn't a predictive state. This is just a column activation based on a spatial pattern. So there's not a prediction occurring here. This is just a mapping. Now, the mapping does change over time because the mapping improves as it learns what portions of that input space are lighting up, and different columns get customized to look at different features in that input space. So all these columns are going to have overlapping receptive fields to the input space, and some of them may be representing the exact same things, or not usually exact, but something very similar. But we can enforce that sparsity just by drawing that line of how many columns how many of the top X columns we want to turn on based on the input. Yeah.
So you said you chose, I think it was like 5 and 6 that can you tell us about how you chose them?
Well, I didn't, you mean for research?
For research or modeling?
So what I've shown you here is one layer called layer 2-3. And that was, I think, chosen because we knew it was involved in sequence memory. And we knew sequence memory was really important. And it was something that current AI techniques aren't necessarily very good at, temporal sequences over time. We do really awesome at spatial recognition, but finding anomalies in things over time is harder. So the types of methods we use are like LSTM is one of the big ones now that does that type of analysis. But even then, it does have to be batch trained again, over time as things change. And we know the brain doesn't have to be batch trained. So we were trying to find what part of that included sequence memory, and it was layer 2-3. And that's commonly thought in neuroscience, that layer 2-3 is a sequence memory operation. Layers 4 and I am not a neuroscientist. Layers 4 and 5, I think 5 is involved with motor command output, and 4 we think is object recognition and retrieval, using the same memory algorithm that is used in 2-3, which is the interesting thing. We think it's close. So there are some differences between the different layers in the cortex. Like, for example, 2-3 has higher cell activations than layer 4 that's doing object recognition. And I think we have ideas about that, but honestly, this is a research area. So we have, in addition to our open source code bases that's running all the visualizations that you just saw, we have research repositories that are open source too, so you can see the type of work we're trying to do with sequence memory and sensory motor integration as well. So there's a few people that keep up on that and ask us questions, but it's kind of hard to follow because we're doing the research at the same time. Okay. Any other questions? Okay, if you want to go to this HDM social, let me know. Thank you.